All right, next up we have phase diagrams. A phase diagram is a graph of pressure versus temperature for a substance. If you turn the page in your notes, I believe you'll have some room to draw. So draw something like this. There's also a couple in your book on pages 432 and 433, but you can draw one like this is fine. So a couple things, let's label some stuff on here. At low temperatures, low temperatures, a substance is likely to exist as a solid. So over here, kind of to the left of these lines, the substance is a solid. So whatever, say this temperature and this pressure. At very high substances, sorry, that did not make sense. At very high temperatures, a substance is likely to exist as a gas. So anywhere to the right of this line here, I know it's a curve, but we call it a line. The substance is a gas, and then in between solid and gas, we have liquid. So for example, at this temperature and this pressure, the substance would be a liquid. At this temperature and this pressure, the substance would be a gas. At this temperature and this pressure, the substance would be a solid. So we can use a phase diagram to determine the state of matter of a substance given its temperature and pressure. Again, so brings up a question. What state of matter is water? Well, it's a trick question. Water can be solid, liquid, or gas, depending on both the temperature and the pressure. Yeah, we'll get some more on that in just a bit. All right, number one says each line represents the temperature and pressure at which two phases may exist in equilibrium. So this line here, which is labeled A on this graph, the line between solid and gas, those are all of the temperatures and pressures where the substance exists simultaneously as a solid and a gas. By the way, going from here to here, what happens to the substance? Well, it changes directly from a solid to a gas or a gas to a solid. That change is called sublimation or deposition, respectively. Let's take a look at this next line here, label B. So that is the line between solid and liquid. So at all of these temperatures and pressures, the substance would exist simultaneously as a solid and a liquid. Have you ever seen solid and liquid water together at the same time? Well, if you've ever had a glass of ice water, that's exactly what's going on. You have solid and liquid water together. And then going across this line, solid to liquid, liquid to solid, left to right, that's melting, right to left, that is freezing. And then lastly, this line here, C, is the line between liquid and gas. So at all of these temperatures and pressures, the substance is simultaneously a liquid and a gas. So let's go back to a question I asked a couple lessons ago. At what temperature does water boil? Go ahead and answer that now. Well, boiling is when a liquid turns into a gas. As we can see here, and I'll show you the phase diagram for water in a little bit, this line here represents all of the different boiling points of water. So notice that as the pressure increases, the temperature at which the liquid becomes a gas also increases. And so we can't say what the temperature of boiling water is. It depends on the pressure, as we talked about the other day. The middle point, so let's go back here. This middle point, D, label D, where all three lines intersect, this is where the substance exists simultaneously as a solid, a liquid, and a gas. This is known as the triple point. If you look in the textbook on page 432, the triple point for water occurs at a very low temperature, just above zero, so 0.01 degrees Celsius. More striking than that is the pressure. Look at that. The triple point occurs at a pressure of 0.6 kilopascals. Now remember, regular atmospheric pressure is about 101 kilopascals. So we're talking about 100 times less pressure than regular atmospheric pressure at sea level. So probably have not seen solid, liquid, and gaseous water at the same time? Maybe you have. All right, normal boiling point and normal melting or freezing point may be determined by drawing a straight line at 1 atmosphere. Remember, normal boiling point is the temperature at which a liquid boils at 1 atmosphere pressure. 1 atmosphere horizontally across the diagram. The temperatures where this line intersects the two other lines, the solid liquid line we call it, and the liquid gas line, are the normal boiling point if it's the line between liquid and gas, and normal melting point if it's the line between solid and liquid. Let me show you. Look here, let's say this is 1 atmosphere pressure. So what we're going to do is we're going to draw, I'll just make it kind of a dotted line all the way across the diagram. And then where the line, horizontal line, crosses the liquid gas line, this would be the normal boiling, whoops, let's see if I can write on there. Normal boiling point. And then this here would be the normal melting point or freezing point. Whatever this temperature is, that's the normal melting point. Whatever that temperature is, that's the normal boiling point. Again, if you look in your book, page 432, at 101.325 kilopascals regular atmospheric pressure, we see that the solid liquid line there intersects that line at 0 degrees Celsius. So that is the normal boiling point of water. And then liquid gas line, that occurs at 100 degrees Celsius. All right, so let's take a look at this now. Let's look specifically at the solid liquid line. The slope of that line can be used to determine if the solid phase or liquid phase is more dense. So let me show you an example. So we have two phase diagrams here. One that has a negative slope for the solid liquid line, and then one that has a positive slope for the solid liquid line. So here's how it works. If the line has a negative slope, then that means the most dense phase for that substance is a liquid. Now, something else to consider. A substance will exist in its most dense state at high pressures. So if you increase the pressure on a substance enough, it'll form its most dense state of matter. And so I'll show you what I mean by that on the phase diagram on the next slide. Conversely, if the line, the solid liquid line, has a positive slope, then the solid phase is more dense than the liquid phase. All right, so let's take a look. So let's say this is the phase diagram for water. Now remember, water is one of the only substances I know that is more dense as a liquid than as a solid. Most substances on Earth are more dense as a solid. Water is the exception. So let's say you have, I don't know, let's say you have some ice. Let's see if I can draw this in a certain color. Let's say you have some ice. Oh, let's say right here. So 0 degrees Celsius at some low pressure. Well, what if you were to increase the pressure? What would happen? You would end up here. So let me ask you this. How do you melt ice? There's two ways of melting ice. You go this way, where you increase the temperature, or you go this way, and you increase the pressure. Interesting, right? If you increase the pressure on ice, you can cause the ice to melt. This is how ice skates work. Got that really thin blade, pushes down hard on the ice, enough pressure to melt the ice so it's a liquid right underneath the skate, and then that skate can move along the ice rather frictionless. So let's look on this diagram. So let's say you are right here. We have liquid liquid of this substance. How do you turn a liquid into a solid? And we're talking about substances other than water. Well, we can decrease the temperature. That would turn a liquid into a solid. Or we can increase the pressure. So that's for substances, again, other than water. So just know that melting can be achieved by changing the temperature or changing the pressure, and that works for both water and for any other substance. Let's change it up a little bit and talk about energy. We've introduced energy before, and so we're going to circle back and do some more stuff with energy. Let's again start though with a review of temperature. Remember, temperature is a measure of the average kinetic energy of the particles in an object. When an object changes physical states, so when a substance undergoes a phase change, as it's called, melting, freezing, boiling, condensing, deposition, the energy that is absorbed or released, so absorbed if it's an endothermic process like melting or boiling, released if it's an exothermic process like freezing or condensing. The energy involved in that process, the energy involved in a phase change, is in the form of potential energy. In fact, when a substance undergoes a phase change, its kinetic energy is constant. There is no change in kinetic energy. There is no change in temperature. We talked about this the other day. When water boils, its temperature does not change during that boiling process. And so since there's no change in temperature, there's no change in kinetic energy. The energy that's involved must be in the form of potential energy. Energy, whether it's kinetic or potential, is measured in the SI unit of joules, a symbol for joules, capital J. The unit we use in the United States for energy is a calorie. So calories in the United States, joules we use in science. Remember that an endothermic process is any process where energy is absorbed from the surroundings. Add that to your notes. Exothermic process is any process where energy is released to the surroundings. So what if a substance is undergoing a change in temperature and not a phase change, just a change in temperature? We can use the specific heat to determine how much energy is involved in that change. So let's start with definition again. Specific heat is the amount of energy required or released, again, depending on if it's an exothermic process. Whoops, got that backwards. Required if it's an endothermic process, and released if it's an exothermic process. So the amount of energy, let me read the first part. The amount of energy required to change the temperature of 1 gram of a substance by 1 degree Celsius. Let me restate that. Specific heat is the amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. So heating is an endothermic process. Let me state it another way. Specific heat is the amount of energy released when the temperature decreases. The temperature of 1 gram of a substance decreases by 1 degree Celsius. So cooling is an exothermic process. So energies in joules, we have mass in grams, we have temperature in Celsius. The units for specific heat are joules per gram degree Celsius. So as mentioned before, when a substance undergoes a change in temperature, increase or decrease, and remains in the same state, the specific heat may be used to calculate the amount of energy involved. Does anybody remember the equation we use that has specific heat in it? It's this one. Q equals MCAT, where Q is the energy absorbed or released by the substance, depending if it's heating or cooling. M is the mass of the substance, that is heating or cooling. C is the specific heat of the substance, that is, guess what? Heating or cooling. And delta T is how much the temperature goes up by if it is being, that's right, heated, or the amount that the temperature goes down by if the substance is, that's right, cooling. Specific heat of water, if you recall, we'll go 3 sig figs here. I know I probably gave it to you 4 sig figs last time. 4.18 or 4.184 joules per gram degree Celsius. Also 1.00 calories per gram degree Celsius, in case we're doing anything with calories. There's a table in the back of your book, has specific heats and all kinds of other data for all of the elements. So you may, sorry about that, you may need to refer to that table. All right, let's take a look at some examples. Calculate the quantity of heat in kilojoules needed to warm water from 25.0 degrees Celsius to 95.0 degrees Celsius. The cup holds 125 milliliters of water. Remember, the density of water is 1.00 grams per milliliter. So each milliliter of water has a mass of 1 gram. So 125 milliliters is 125 grams. So let's set that up. So that's our mass. Specific heat, 4.18. Don't forget the units. And then our change in temperature. Remember, we said that delta T technically is calculated TF minus TI. Final temperature minus initial temperature. We only have to use this, though, if we're looking for either TF or TI. So in every other situation, we'll just take the absolute value of the difference in temperatures. So I'm going to go bigger minus smaller just to keep my value positive. And I'm going to show this, I'm going to include this in the work. You can calculate this separately if you wanted. Be careful with your sig figs. We have a mixed operations calculation where we're doing subtraction here and then multiplication here. All right, go ahead and pause the video and punch that up, see what you get. Looks like you get something like 36,575 joules. Notice that's the grams cancel, degrees Celsius cancels. When you subtract those, you get 70.0, by the way, which is 3 sig figs. And the question asks for the answer in kilojoules, so we'll take that divided by 1,000, and we get 36.6 kilojoules as our answer. All right, let's go ahead and try this one out. How much energy is required to heat an iron nail, which has a specific heat of 0.44 joules per gram degree Celsius, and a mass of 14 grams from 25 degrees Celsius until it becomes red hot at 750 degrees Celsius. Go ahead and pause the video and do this now. 2 sig figs in our mass, 2 sig figs in our specific heats. Our change in temperature, 725 degrees Celsius. And so we get about 4,500 joules. Divide that by 1,000, 4.5 kilojoules. All right, let's go ahead and try this one at 5,570. Make sure that number's right because I have a different number in my notes. 5,570 joules of energy are added to a 400 gram piece of lead that has a specific heat of 0.13 joules per gram degree Celsius at 24 degrees Celsius. What is the final temperature of the lead? Now, there's a couple different ways you can do this. I'll let you do it. Go ahead and pause and do it now, please. Just here could vary depending on how you did this. If you set it up like I showed you before, where you just put, instead of delta T, you put TF minus TI and solve for TF, you get to 134.6. If you solve for delta T first, that number should have, I believe, 2 sig figs. So that's about 110 degrees Celsius without the decimal. And then take that and add it to your initial temperature, right? So delta T plus TI equals TF, and you get 135 degrees Celsius. All right, one more. Go ahead and try this one. Calculate specific heat. Pause now. Hopefully you notice that's the energy that was given in the problem is in kilojoules. So 1.00 kilojoules, that's 1.00 times 10 to the third joules. Got our mass, got our change in temperature, calculate the specific heat, and we end up with 0.896 joules per gram degree Celsius. All right, that concludes this lesson. I'll give you a chance for some practice with this stuff in just a bit. Thanks for watching.